In this lesson, we're going to introduce electrophilic aromatic substitution, focusing on the halogenation, nitration, and sulfonation reactions of benzene. As we've already seen, benzene is an aromatic molecule, and that aromaticity makes benzene extremely stable. At first glance, benzene looks like an alkene, a triene actually, and we know that alkenes undergo electrophilic addition reactions, adding a molecule across a carbon-carbon pi bond. However, benzene does not undergo electrophilic addition reactions, and that's simply because an addition reaction would disrupt the aromaticity in the benzene structure, making the reaction extremely endergonic and therefore highly disfavored. Instead, benzene undergoes electrophilic aromatic substitution, or EAS. In an EAS reaction, one of the hydrogens on benzene is replaced by an electrophilic atom or group. So here I show the general mechanism of an EAS reaction using XY as a generic electrophile. If you look at the intermediate formed in the reaction, you can see that the aromaticity is temporarily disrupted. This transient loss of aromaticity means that EAS reactions require very powerful electrophiles. So in the first step, benzene acts as a nucleophile. One of the pi bonds attacks the electron-deficient part of the electrophile, forming a new sigma bond and a resonance stabilized carbocation intermediate. In the second step, a weak base removes the proton from the carbon now bonded to the electrophilic atom. The electrons in the CH bond are pushed back into the ring to form a new pi bond, reestablishing aromaticity. The first electrophilic aromatic substitution we're going to explore is EAS halogenation. The reaction substitutes a hydrogen on benzene for a halogen, typically bromine or chlorine. As you can see in the example, the reaction requires one equivalent of a dihalide and a Lewis acid catalyst, usually iron bromide or iron chloride. If we look at the mechanism, we see that the actual EAS reaction is preceded by the formation of a strong electrophilic adduct. In fact, all EAS reactions begin with the formation of some powerful electrophile that sets up the EAS mechanism. In this case, the strong electrophile is formed through a simple Lewis acid-base reaction. The dihalide acts as a Lewis base, donating a lone pair into an empty orbital on the Lewis acid catalyst. The resulting adduct then serves as the electrophile in the EAS reaction. In the first EAS step, benzene acts as a nucleophile, attacking the electron-deficient terminal bromine atom of the electrophile, breaking the bromine-bromine bond and creating a carbon-bromine bond. The resulting resonance-stabilized carbocation is then deprotonated, forming a new carbon-carbon pi bond and re-establishing aromaticity. Next, we have EAS nitration, which substitutes a hydrogen atom on benzene for a nitro group. As you can see in the example, the reaction is typically performed with concentrated nitric and sulfuric acids. If we look at the mechanism, we see that these two acids react with one another to form the electrophile needed for the EAS reaction. The first step is a Bronsted acid-base reaction. The nitric acid acts as a base and is protonated by the sulfuric acid. The resulting conjugate acid expels a molecule of water to form the strongly electrophilic nitronium ion, setting up the EAS part of the mechanism. In the first EAS step, benzene acts as a nucleophile, attacking the electron-deficient nitrogen atom of the nitronium ion, and forcing one of the nitrogen-oxygen pi bonds to break. The resulting resonance-stabilized carbocation is then deprotonated, forming a new carbon-carbon pi bond and re-establishing aromaticity. Next, we have EAS sulfonation, which substitutes a hydrogen atom on benzene for a sulfonic acid group. As you can see in the example, the reaction is performed with hot concentrated sulfuric acid. The sulfonic acid functionality is commonly encountered in synthetic detergents, in the form of a sodium or potassium salt. If you've ever looked at a bottle of shampoo and seen sodium lauryl sulfate or sodium lauranth sulfate, those are just sodium salts of organic sulfonic acids. If we look at the reaction mechanism, we see that the sulfuric acid reacts with itself to form the strong electrophile required for the reaction. The first step is a Bronsted acid-base reaction. One molecule of sulfuric acid is protonated by another. The resulting conjugate acid expels a molecule of water to form the sulfonium ion that serves as the electrophile in the EAS reaction. In the first EAS step, benzene serves as a nucleophile, attacking the electron-deficient sulfur atom of the sulfonium ion. The resulting resonance stabilized carbocation is then deprotonated, forming a new carbon-carbon pi bond and re-establishing aromaticity. The EAS sulfonation reaction is sensitive to the concentration of sulfuric acid used. The sulfonic acid group can actually be removed using dilute sulfuric acid. The ability to introduce and then later remove a sulfonic acid group from a benzene can actually be synthetically useful. The sulfonic acid group can be used to temporarily influence the regioselectivity of other EAS reactions in a multi-step synthesis.